In seeking knowledge thou art wise. In imagining that thou hast attained it, thou art a fool. From the Talmud. This is some kind of an adventure game for a single player, namely you. But you can only win by learning to understand basic physical principles and their representation in equations, and by rejecting to be suffocated by dogmas from belief systems. Is dihydrogen oxide a greenhouse gas? Obviously not, if it is embedded in the hydrosphere, which is dominated by the oceans. As the only planet in our solar system, the Earth has, so to speak, two atmospheres. A gaseous one, the actual atmosphere, and an inverted, liquid, condensed one, the hydrosphere, which only partially covers the surface of the planet. Both atmospheres require proper modeling. This paper deals with and analyzes some assumptions used in the calculation of the Earth's radiation balance and proposes a simple corrected model in which the role of the hydrosphere is adequately reflected. Written on a popular science level, it is some kind of experiment with basic physical principles and their representation in equations. By correctly taking into account fundamental properties of radiation, we show that the difference between the observed temperature of the Earth and the well-known calculated temperature for an Earth without atmosphere, 33 degrees Kelvin, is mostly exhausted by the contribution of the hydrosphere. Introduction. When several forms of energy, interactions, forces, are involved in a physical problem, the method of choice is a thermodynamic perspective. Hence, for the climate system, a framework of investigation based upon macroscopic non-equilibrium thermodynamics is favorable. As a future perspective, non-equilibrium statistical mechanics offers the tools for a more fundamental approach along the lines of modern physics. In this paper, we do not discuss the foregoing arguments, but assume that the radiation balance equation is a suitable tool for the description and calculation of overall effects on the Earth's average temperature, so far as this tool is used with suitable assumptions and approximations. Special attention is given to the role of the hydrosphere, which here is approximated by the oceans, which cover 71% of the Earth's surface, with a depth span from 0 to about 11,000 meters and an average depth of 3,800 meters. Descriptive properties of radiation physics used in this paper are temperature T, area A, power P, that is energy per time unit, and power density I per square unit. Case 1. Earth without atmosphere. The overall radiation balance of the Earth without atmosphere is usually calculated as follows. The Sun is modeled as a blackbody irradiator with an effective temperature of about 5,800 degrees Kelvin, that is, with the average temperature of a suitable layer of its photosphere. Then, with the Stefan-Boltzmann constant sigma, the Sun radiates a power density, power per square unit, uniformly into all directions, which can be calculated by the Stefan-Boltzmann law as I equals to sigma times T to the fourth. The Earth receives a small part, namely the solar irradiance, solar constant, S equal to 1368 watts per square meter, which is incident on the cross-sectional area perpendicular to the incoming radiation, leading to an incoming power pi r square times S times 1 minus alpha. Here, alpha denotes the average reflectivity, the albedo of the Earth, which is usually set to 0.31. As we are generally dealing with averages, we may replace the left-hand side of equation 1 by power in equals to 4 pi r square times S 1/4 times 1 minus alpha. With the fourth part of the solar constant S 1/4 now distributed to the whole spherical surface, 4 pi r square. Note, we may play with area sizes as long as the product power density times area remains constant. In the absence of other energy sinks or sources, the balance power in equals power out holds, where the outgoing power is modeled by 4 pi r square times sigma times T to the fourth. This term shows that the Earth is considered as a black body irradiator with temperature T and a radiating spherical surface 4 pi r square. All quantities referring to the Earth except alpha, r and s are tagged with a subscript E. The radiation balance equation then is given in full by equation 3. Eliminating the surface of the Earth on both sides and solving for T yields the equation for the temperature of the Earth, TE, with a well-known numerical result, 254 degrees Kelvin equal to minus 19 degrees Celsius. Interlude: Analysis of assumptions and approximations. In the Earth energy budget diagram of NASA, see left side, 6.7% of the incoming solar radiation is reflected by the Earth's surface, while 22.6% reflection stems from the atmosphere, including clouds. In case 1 we used an albedo of 0.31. Note, this value includes the atmospheric part of the albedo, so take the notion Earth without atmosphere with a grain of salt. What is the reason behind the choice alpha equals 0.31 in case 1? It is the assumption that the atmosphere has the first choice with respect to reflection, and hence, without atmosphere, its 22.6% part would be reflected later by the surface, the second choice, in addition to its own 6.7%, yielding in total 29.3%, about 0.31. We here ignore small numerical differences in order to keep in line with earlier values. But we can also take to an alternative, minimal assumption. Without atmosphere, only 6.7% of the incident solar radiation is reflected by the Earth's surface, that is, alpha star equals 0.067, while 22.6% is absorbed by the surface. From this viewpoint, we may reinterpret case 1 as the Earth without atmosphere, but with the cooling effect of the atmosphere, provided by an increased albedo 0.31 greater than 0.067. It is beyond the scope of this paper to discuss the realism of any of these assumptions, which define a span, that is, alpha lies between 0.067 and 0.31. Instead, we define a case 1 star with the alternative value alpha star equals 0.067. From equation 4 applied twice, we then obtain a simple relation for the corresponding temperature as a function of alpha star, namely equation 5. Then we obtain for the temperature T E star 274 degrees Kelvin, or about 1 degree Celsius. For further comparison, we define a case 0. The minimal albedo for the Earth as a perfect blackbody radiator is alpha blackbody equals to 0, yielding a temperature of 279 degrees Kelvin, or about 6 degrees Celsius. Case 2. Earth without hydrosphere and without atmosphere. What did we really calculate in case 1? Is it the Earth with oceans, that is, with a hydrosphere, which in this paper is always approximated by its oceans? If so, we simply remove the oceans and replace their former bottoms by a thin layer with the same albedo as the oceans, such that the average albedo remains unchanged at 0.31. Then 100% of the Earth's surface is now covered by land. As no changes occur in the calculated resulting temperature, we find that case 1 is really the case without hydrosphere and without atmosphere, apart from the atmospheric contribution to the average albedo, as already mentioned before, and not, as wrongly denoted, the case without atmosphere. Hence, case 1 and case 2 are the same. Earth with hydrosphere but without atmosphere. Starting with case 1 or 2, we now fill or refill the oceanic pools with a condensed greenhouse gas, dihydrogen oxide, until 71% of the Earth's surface are again covered by oceans. Both in liquid and vapor phase, water is an isotropic infrared radiator, of course with different attenuation lengths, respectively absorption coefficients. See next slide. Isotropy means that there is re-emission with direction components both to outer space and to the bottom of the oceans, each with 50%. In this water absorption spectrum, the absorption coefficient for water is shown for the wavelength domain between 667 nanometers and 200 micrometers, that is, from visible red and the most important part of infrared light. The red line refers to the liquid phase, the green line to the vapor, and the blue line to the ice phase of water. It follows that the whole oceanic area radiates with half power density towards outer space, or half the oceanic area with full power density. We choose the latter case and modify the radiating area to alpha EO equals 4 pi r square times 1/2 times 71% plus 29%, which is equal to 0.645 times the surface of the Earth. All quantities referring to the Earth with hydrosphere are tagged with a subscript EO. The right-hand side of equation 3, the radiation balance equation applied to case 1, is then replaced by another term, namely equation 7. As equation 3 represents a conservation law, with the value of the left-hand side fixed, it is evident that the smaller radiating area on the right-hand side forces a higher power density, sigma times T to the fourth, and hence a higher temperature T. Then we obtain for the temperature TEO 283 degrees Kelvin, what is about 10 degrees Celsius. Hence, the existence of a hydrosphere covering 71% of the Earth's surface raises the average temperature by 29 degrees Kelvin. For detail-oriented people, cover the oceans with a thin and, with respect to visual and infrared light, transparent foil or layer in order to prevent sublimation of the water. Just for completeness, we add a case 3 star with a lower albedo, alpha star equal to 0.067. Then we obtain a temperature TE star O equals to 306 degrees Kelvin or approximately 33 degrees Celsius, and a difference between 33 degrees Celsius and 1 degree Celsius of 32 degrees Kelvin. This unrealistic result does not recommend the choice of alpha star equal to 0.067. Case 4. Deep sea variant of case 3. The red line for liquid water in the water absorption spectrum is now shown in the next slide in more detail, from 10 nanometers ultraviolet to more than 1 millimeter, that is more than 1000 nanometers, far infrared. The minimal absorption occurs in the visible part of the spectrum, which is the cause for the transparency of the shallow sea part of the oceans. The notion deep sea describes those parts of the oceans with depth more than 200 meters. Then the visible spectrum is fully absorbed. Hence one could argue that at least part of the reflected light from the non-deep shallow sea is already contained in the albedo, and that there is lesser infrared re-emission. As an unrealistic overdone estimate of this effect, we assume that with respect to reflection and absorption, the shallow sea behaves as if it were a piece of land. In other words, isotropic radiation is restricted to the deep sea zones of the oceans. They amount to 88% of 71%, that is to 62.5% of the Earth's surface. The remaining land and shallow sea areas cover 37.5%. All quantities referring to this variant are tagged with the subscript EO-. The radiating area is now modified by a factor of 0.687, see equation 10. For the corresponding temperature, TEO-, we obtain 6 degrees Celsius instead of 10 degrees Celsius and a temperature difference of 25 degrees Kelvin instead of 29 degrees Kelvin. It is clear that a more realistic approximation must distribute the shallow sea part, 12% of 71%, that is 8.52%, to both the oceans and the land in a suitable way. For example, for equipartition we get a factor of 0.666, which is just the middle between the foregoing results. As we may linearly interpolate between the multipliers of TE for small changes in the multipliers of the area, we obtain TEO- modified of 8 degrees Celsius and a difference of 27 degrees Kelvin. We omit the equipartition case from further calculations, as linear interpolation between results of the two oceanic variants is always possible. Again, for completeness, we add a case for star, that is the deep sea with the lower albedo. Then we obtain for the temperature 28 degrees Celsius and a temperature difference of 27 degrees Kelvin. Case 5. Earth with both hydrosphere and atmosphere. All quantities referring to the Earth with hydrosphere and atmosphere are tagged with the subscript EOR. The observed average temperature of this system is 14 degrees Celsius. Whereas formerly the temperature difference of 33 degrees Kelvin is exclusively attributed to the atmosphere by the presence of the oceans, the effect is now reduced to 4 degrees Kelvin. And in the deep sea case, the maximal difference is 8 degrees Kelvin. Case 6. Albedo. Which albedo reduction makes the atmosphere unnecessary when we want to obtain a temperature equal to the observed 14 degrees Celsius? We here skip the technical details and discuss the results in the section Results and Conclusions. Case 7. Earth with atmospheric effect, but with oceanic effect removed. Again, we discuss the results in what follows. Results and conclusions. Let us begin with a survey of the numerical results for all cases shown in Table 1. Case 0 describes the Earth as a perfect black body with zero albedo, that is maximal warming, and we come out with a temperature of 279 degrees Kelvin or 6 degrees Celsius. Case 1 equals Case 2 and describes the Earth without oceans and without atmosphere, but nevertheless with atmospheric albedo alpha equal to 0.31. This case comes out with a temperature of -19 degrees Celsius and is the reference case for further calculations. Case 1 star is the same as case 1, but with a reduced albedo alpha equal to 0.067. That is, the atmospheric part is fully subtracted as discussed in case 1, and we obtain a temperature of 1 degree Celsius. All further cases tagged with a star will use this reduced albedo and case 1 star as a reference case. It is clear that for an Earth strictly without an atmosphere, a realistic albedo must have a value between 0.067 and 0.31, and hence a temperature between -19 and +1 degree Celsius. Now we come to the cases where the hydrosphere, modeled by the oceans, plays an important role. In case 3, we consider an Earth with 71% of its surface covered by oceans, with isotropic re-emission of absorbed infrared light by the whole ocean area. Then we obtain a temperature of 10 degrees Celsius. In case 4, we consider only the deep sea part of the oceans and come out with 6 degrees Celsius. Hence, a realistic result lies somewhere between the two values 6 and 10 degrees Celsius. For example, if we take cases 3 and 4 with equal weight, we obtain 8 degrees Celsius. Recalculations of cases 3 and 4 with a lower albedo 0.067 result in temperatures of 33 degrees Celsius in the ocean area case 3 star and of 28 degrees Celsius in the deep sea only case 4 star. In both cases, cooling by the atmosphere is required if we want to obtain the observed Earth temperature of 14 degrees Celsius. Case 5 refers to the Earth with both oceans and atmosphere and with the observed 14 degrees Celsius. Note that the temperature difference between the reference case 1 and the observed case 5 is 33 degrees Kelvin or Celsius. Temperature differences relative to the reference case are shown in table column delta in degrees Kelvin. The ocean area case 3 comes out with 29 degrees Kelvin, whereas the deep sea case 4 yields 25 degrees Kelvin. In case 6, we determine in the two ocean cases 3 and 4 the, of course, reduced albedo, which is necessary for a temperature increase to 14 degrees Celsius without any contribution from the atmosphere. The results are 0.27 for the full ocean area case and 0.23 for the deep sea case. Finally, in case 7, we consider the Earth with atmosphere but without oceans by removing the temperature effect of the oceans numerically. This is done by calculating relative powers. See table column with header P rel, namely by normalizing the power in case 5 with a temperature of 14 degrees Celsius to 100%. Then differences in relative powers correspond to differences in temperatures T, as P rel is proportional to the fourth power of temperatures T measured in degrees Kelvin. As a result, the relative powers are 66.3% for the oceanless ocean area case and 72.2% for the oceanless deep sea case, which correspond to temperatures of -14 and -8 degrees Celsius respectively. It follows that within this model the existence of oceans is absolutely necessary for Earth temperatures above 0 degrees Celsius. First of all, the water molecule is an infrared active molecule and it does not lose this property when embedded in water. In its condensed liquid phase, it even gains further domains of infrared activity caused by the excitations of hydrogen bonds. Of course, water as a liquid is not a gas, but the task of physics as a natural science is not to impress by wordings, but to model physical properties adequately. By correctly taking into account fundamental properties of radiation, we show that the difference between the observed temperature of the Earth and the well-known calculated temperature for an Earth without atmosphere, 33 degrees Kelvin, is mostly exhausted by the contribution of the hydrosphere, namely 29 degrees Kelvin, which leaves a remainder of 4 degrees Kelvin for the contribution of the atmosphere. This is a reduction by almost one order of magnitude. The corresponding values for the two deep sea approximations are: shallow sea behaves like land, yields 25 degrees Kelvin with a remainder of 8 degrees Kelvin, and equipartition gives 27 degrees Kelvin with 6 degrees Kelvin as a difference. Surprisingly, the basic property of isotropy for the radiation re-emission of dihydrogen oxide turns out to be already sufficient to force a plausible result with respect to the contribution of the hydrosphere to the average planet temperature. Note that the exceptional feature of this planet is by no means an atmosphere. Also other planets have it, in different forms. But the existence of two atmospheres, an ordinary gaseous atmosphere and a condensed one, the hydrosphere, which, with respect to Earth's surface, is an upside-down atmosphere. Perhaps this feature, together with an incomplete covering of 71%, that is 29% land holes, further impairs such a classification. By the way, about 4 billion years ago, the atmosphere of the hot Earth consisted of about 80% of a wet water vapor, until the Earth became sufficiently cold so that by condensation and precipitation for several hundreds to thousands of years, the oceans came into existence. It is also the oceans that have played the decisive role for the emergence of life. To sum up, it is all the more surprising that this issue escaped attention for so long, and the discussion of the infrared active greenhouse gas dihydrogen oxide is still kept focused on the real atmosphere. This paper is dedicated to those who want to understand the greenhouse effect in full. If you accept the atmospheric part of the greenhouse effect, why do you forget, neglect, or even deny the hydrospheric part? Thank you. The original paper contains an addendum derivation of an extended radiation balance equation, which is omitted in the video.